This video covers mechanical energies. We have three different mechanical energies. Our first one is kinetic energy. This energy comes from the moving of masses, and our unit for energy is joules. One of the most important things to remember about energy is that energy is a scalar, meaning that it does not have direction. In this case, kinetic energy can never be negative because the only place it would have gotten a negative would have been from velocity, and velocity is being squared. So this is actually called speed rather than velocity. So again, kinetic energy will always be positive, and energy itself is a scalar. Here we're talking about potential energy in general. Potential energy is the energy related to an object's position. Consider it as a potential to create speed and kinetic energy. So we have two different types of potential energy, and we'll see the first one in the next part. Our first type of potential energy is gravitational potential energy. To have gravitational potential energy, an object needs to have height. Now, in kinetic energy, our negative always went away. In this case, if we have a negative height, then we can have a negative potential energy. So, the easiest place to put the coordinate axis is at the lowest point a mass will ever reach during a problem. Then that makes all of our heights positive. Our second potential energy comes from springs, but before we can look at that, we need to look at the force of a spring. So here we're looking at Hooke's law. Hooke's law tells us that the force of a spring is equal to the negative k, which is our spring constant, times x, our displacement. Springs, rubber bands, the string on a bow, and arrow set pendulums, all of these experience a restoring force. What that means is that every time that you move this object, it always wants to go back to the way it was at the beginning. Now let's look at that equation a little bit more. That negative basically tells us that our spring force is always opposite the direction of the displacement. So what that means is if we look at this first situation down here, I have this dotted line that goes down the center. That's telling us that this is equilibrium. There are no forces acting on it. My spring is at rest. In the second situation, that's a 2. In the second situation, that dotted line again tells me it's my equilibrium, but I have a force being applied. I'm pulling my object to the right. As you can see, the displacement will be a positive number. So again, we're being displaced to the right. So what my spring wants to do is it wants to pull it back to its equilibrium position. So it wants to pull it back to the left. So again, that's what that negative is telling us. In the third situation, again, my dotted line is my equilibrium. I have a force being applied to the left, meaning I'm pushing my object backwards. So my displacement is going to be a negative number, but what the spring is doing, it's actually pushing against it. It's actually pushing in the positive direction. So what that negative tells us, it's always opposite the direction of motion or displacement. So when you are calculating these values, you can basically ignore that negative for the most part. But when you are graphing, like you'll see in a little bit, you're going to need to keep that negative there. So let's say you want to determine the spring constant, and you have this spring hanging from the ceiling. Now, when there's nothing on it, we know that this object or this spring is at rest. If I hang a mass on it, like in this second picture, so this is without the mass, this is with the mass, now we can see that my object, or my spring, has been displaced this distance. So if I look at my Hooke's law, what this tells us is that we can use this information to help us find the spring constant. So again, if I know that my object has reached another equilibrium position, so I've put this mass on the spring, now it has come to a stop over here, that my downward force, my gravitational force, is equal to my upward force, which is my spring force in this case. So that means that my spring force minus my gravitational force is equal to 0. Again, it's at rest. which means my spring force is equal to my gravitational force, which means that mg is equal to k times x. Again, here we want to ignore that negative because we know that that is just telling us that my spring force is opposite the direction of the displacement. So, here, if I'm asked to solve for the spring constant, which is k, I simply divide by the distance it was displaced. So it would be simply equal to mg divided by x. Now, if you're asked to graph Hooke's law, or if you're looking at a graph of force and displacement, then you cannot ignore that negative. So let's say you have a situation where k is equal to 10 newtons per meter. Here, we know that our force of our spring is equal to negative kx, so I can put a negative 10, and here in this situation we don't have any displacement, so our force of a spring would be equal to 0. Let's say that my object has now been displaced 2 meters, then my force of the spring is now negative 20 newtons. If it's displaced 4 meters, then it is a spring force of negative 40. So you should start to notice that proportional relationship. As x increases, so does my spring force. Again, noticing that linear relationship between force and displacement, I can see that if I plotted this information, that the slope actually tells me my spring constant. So keep that in mind anytime that you look at a graph. Does the slope tell me anything? So now looking at elastic potential energy. The potential energy stored in elastic objects when they are stretched or compressed from their equilibrium position. Now there's two very important conditions for this. A spring or other elastic object must be stretched or compressed. That's where our x value comes in. But it also must be able to move if it is released, and we'll see an example of that in a second. In this example, a 100-gram mass is attached to a spring and is lowered 25 centimeters until it reaches equilibrium. It's asking to determine the spring constant. Again, when it reaches that equilibrium position, our force of our spring, which is upwards, is going to equal our gravitational force, which is downwards. So, kx is equal to mg. If we want to solve for the spring constant, again, that would be k is equal to mg over x. Making sure that we change that mass to kilograms. We can use 10 here, that's okay. And our centimeters has been changed to meters. So we should get a value of 4 newtons per meter. Now, it asks us to also determine the potential energy stored in the spring. Now, again, you might go through the process and try to solve for the potential energy, but if this object is at equilibrium and I let it go, and it does not move, then it had no elastic potential energy. So, the potential energy would actually be equal to 0. Again, when you have equilibrium forces, meaning that things are balanced and equal, it will not move when it is released. So, the presence of a spring, even a stretched spring, is not enough. It has to be able to move when released. Now let's say that you have that exact same situation, but after it's reached equilibrium, you have stretched it an additional 10 centimeters. Now that you have stretched it, now we know that when you release it, it will be able to move. So it can have elastic potential energy. So our equation was 1/2 kx squared. In this case, we're not considering the entire distance stretch. It is not 35 centimeters because, again, that will not give us a potential energy. It is only that 10 centimeters. We calculated our gravitational constant, spring constant, and our 10 centimeters is what it's being stretched. So then it has an energy of 0.02, and it's joules. 0.02 joules. And the last part, if a problem asks you to solve for the total mechanical energy, well, we have three types of mechanical energy. We have kinetic potential energy of a spring and gravitational potential energy. So we would simply need to add all three up. This is going to help us go into our next section, which talks about conservation of mechanical energy.